understand.
Yo. 15? I think 15 is good. Let's see. Remove the overlay. This should be good. Why am I mini? That's mini me. Why is that mini me? This should be better. Maybe. Yeah. I'm getting rid of the starting soon. Hola. Hey, hola. I'm from Mexico, so hey, hola. Hey, beep beep. Hey, Light Warrior. Hey, Ibrahim. Hey, Happy. And Arnav. Cool. And nice. We have some people watching. Cool. Okay, let's get started. Let's see. Where should I start? Maybe first thing should be I have to share this link with you to register. Let me just double check that. Let's see if that works, because the link was way longer. Yeah, it works. Okay, cool. So that should work. For some reason, it gives me a very long link, and I just shorten it there, but it should work. Nice. Okay, so I'll share my entire screen. I think that's the best thing to do. Yep, there we go. Hey, cool. Should be there. Yeah, nice. Let's get started. Cool. Well, welcome to Train an Autonomous Vehicle with PyBullet. Checked in. Awesome. Thank you. Why? Nice. So, well, who am I? I need to update that picture. That picture has like nearly 4 years. But yeah, yeah, I feel you, Spartan. Lots of things sometimes you overload your brain with information and it's just too much. But yeah, a little bit of PyBullet won't do any damage. Cool. Well, that's me. My name is Charbel. People call me Bully. I'm a robotics and telecommunications engineer. I live in Puebla, Mexico. I was a fellow for the I think it was the second production engineering batch in 2021. I've been a pod leader ever since 2022. I'm a program coordinator since 2025, and I probably need to remove my university, but I studied at UDLAP, which is a cool university here in Mexico. Why is it killing you? Is it too loud? No? Why? Should I just maybe like that? Is that better? Cool. Okay. If you want to connect with me, there's my GitHub, my LinkedIn, my Discord, and my email, just in case. Okay. Well, yeah, that's a little bit about me. And I'm 24. Yeah, I think so. Yeah, 24. Cool. Okay, so this is Train an Autonomous Vehicle with PyBullet Part 1. Okay. Starting with what's PyBullet? Like, that sounds interesting. What does a bullet to be API 6 p.m.? What do you mean API 6 p.m.? It's 6 p.m., right? EST. I'm not sure. But cool. Okay, yeah. Well, what is PyBullet? PyBullet is a oh well, hello. It's a framework that works in really? Don't say that. Let me see if I just got it wrong. If I got it wrong and I just removed someone's, let me not show Slack here. Let's see. Let me do something real quick. Now, Jason? If you're right, I hope not. Where's Bia? Bia. Blah, blah, blah. Here it is. Should be okay. No. Okay, so now it should be me, and then should be an empty slot, and then we should have a building a persistent memory MCP server part 1, and then a part 2 of that. Wait, what? Is today Friday? Today's Friday. What the heck? Really? Then okay. API week, or okay. Then the schedule is wrong. Let me just flag that. Thanks so much. Yeah. Hey, Quakers. Okay. Where's the schedule? You shared it here, right? Okay. Global Hack Week. So give me a moment. Let's see this. Let me share this one. Yep, they won. Yep. No, here it is, right? Oh, I mean, oh, wait a minute. What? It's supposed to be tomorrow, 10 a.m. GMT. Okay. So it's an error in the schedule. Okay. Yeah. Okay. So our bad. I should be now. I have like the back end schedule, and that should be good. Like this schedule is back. Okay. So I'll just flag it. Thanks so much for letting us know. Yeah. Okay. You know what? Let's just go over it. I'll just message my colleagues at MLH. Yeah, see here? This is me. Okay, maybe I shouldn't show this, but yeah. Not even Slack. Yeah. Thank you, Quakers. Let's just do it. If you don't see me streaming anymore, it's probably because Mary just threw a chair at me and I can't move anymore. But yeah, as far as I know, like it's my time right now. Oh, hey Tammy, how's it going? Yeah. I don't know. Let's just do it. Why not? Cool. Okay, so what's PyBullet? PyBullet is a physics simulator for robotics. Mary will go WWE on me. I hope she doesn't. If this is my time, she won't. If you see me with the bandage on my head or something, she just threw a chair on me or something. Okay, cool. So, nice. If you want to start with robotics and you feel like, hey, I need to buy a robot or something, this is not for me. Give it a try. It's 4 a.m. Saturday in India. Thanks so much for staying, Arnav. Maybe a bug. I don't know. Cool. Okay, so you can use a lot of robots, train them, simulate them, everything done by a simulator in your computer using Python. Nothing else but Python. Okay, and this is the real deal. You have something called ROS. ROS is the robotics operating system. It's an open source operating system that most startup robot companies use when you are in a different stage, like you're just going from a startup to a well-defined company. Usually companies create their own operating system or modify ROS, okay? So PyBullet is kind of based on ROS. You don't need Linux. You can run it in Windows, fine, okay? Cool. So like, okay, why PyBullet? Like, yeah, sure, it's cool. You saw that it's backed by Meta. Why? It reduces costs of training and programming, so you don't need to buy anything. Just have Python, which is free. It makes it easier to understand the backbone of a robot, and you can train in swarms for free. So, close up. What do I mean for free? So, when you're training a robot, things usually don't go as you expect. So, the robot might fall if it's a humanoid. It might crash if it's a car or a drone. And you might break it. And that takes time and money. And the best way to do it is to do it in a simulator and just grab the same information that you used simulating, sending it to your robot, should work the same. Yeah. There you go. Quicker says you need to simulate your robot's operations so you don't accidentally cut people's arms off. Close up time again. True story. 2-ish years ago, we were at the autonomous drone competition. Our drone was trained. Our drone was programmed. I did the computer vision. Yep. Everything worked. The robot, like the drone, flew. It hovered a bit. And then something smelled fishy. And I was like, yeah, turn it off. Let's just try it again. And we did Control C on the terminal, which is like secterm, which is, turn everything off. And the drone just decided to go all Terminator and saying, I won't turn off. So the drone stayed hovering for like 30 seconds. And then something happened with the control system that it started to go forward. Even though we were Control C every time, it wouldn't stop. We had to, it went all the way directly to my friend and he cut his finger off. so yeah, careful with drones. But yeah, it's I guess robots are fun if you, yeah. Is there a backend solution? What do you mean by backend solution? Okay, just what do you mean by a backend solution there? The ETH when your robot flies. Yeah, but you know what? If you Control C, everything should be down. Like everything just goes down, ROS shuts off, and then your robot just immediately just turns off. And it didn't happen. So yeah, that's a finger in the robot that we won't be using. Yeah, outside of Control C. Is there a backend solution? Oh. So ideally, you should have a backend solution, which is like a secterm, or in your code, if you press Q or 1, 2, 3, your drone turns off. And that's what we did after. Like when we debugged, we added that killing switch that even if Control C didn't work, if we wrote 1, 2, 3, it automatically turned off the robot. That was our backend thing. But yeah, we didn't think about it up until we lost a finger, right? Yeah, that was a good question. Like a kill switch, yeah, exactly. Cool. Okay, so basically you use a simulator to do everything free, harm-free, money-free, and you don't use a lot of time with looking for a location to train your robots. Okay. Cool. I'll give you a little bit of context here so you will understand what we'll be working with. Okay. Unified Robot Description Format, also known as URDFs. URDF look like this. Okay. It's a bunch of boxes, cylinders, and pyramids that, let's say, build a robot. So you build your robot with boxes, cylinders, and pyramids. And then it doesn't look like your robot, but it kind of acts like your, as in a video game, it acts like your hitbox. Okay, so you simulate your robot with all three shapes, and then you can just prettify it with putting like a skin on it. So it looks like a robot, but it's actually a bunch of boxes. Okay, so that's what an URDF is. It's an XML file used in ROS. Okay. PyBullet uses it too. We won't be diving into URDFs. It takes time. It defines physical structure like this, like links and joints, and helps you visualize and understand robot physics. Okay, cool. So we'll get to quaternions and Euler angles in a second. Okay, let's just get programming. Yeah, cool. So I don't know, what do you use? I'll use the best of the best, which is Visual Studio. These are my templates, so I won't use this. I'll do. Oh, by the way, before everything starts, let me share with you this. Okay, so here, can you run this in Collab Pro? I don't think so, Tammy. I don't think so because you require, because it's a simulator running. Collab is not good when you use real-time plotting, and this will plot in real time. So I would suggest you can try, but I would suggest you use it in your like locally, Python locally, should work. Okay. Cool. Okay, so the link that I just shared is this one. Okay, it's APIs 2026, and this will contain everything related to the stream part 2 and Pandas 101. Okay, so everything that I stream will be here. Okay, cool, awesome. So let's go to here. Let's do, I don't know, part 1. I'll go to part 1. We'll just open it. There we go. So it's not messy. There we go. Nice. Okay. So as always, okay, people who are veterans to my streams know that I always talk about virtual environments. Okay. A virtual environment is, yeah, it's like a bubble inside of your computer where it contains, in this case, it's a Python environment, which contains different Python libraries that don't coexist with your, let's say, outside Python. Okay, they don't affect your outside Python, which is your base Python. But in case something fails or there are two or some libraries clash, it stays in the bubble. You can just delete it and that's it. Your Python doesn't get like nothing happens to your Python. I resist VMV. I hit it, but I know it's a safety measure. Yeah, always. Because if you start downloading lots of libraries, they'll clash. And it's horrible. You have to go and manually remove them, and it's just a mess. First thing I used to vibe code with ChatGPT was learning how to manipulate files in your files. Yeah, I know, I get it, but you know what? Let's just do a VMV. It takes 2 seconds. Cool, so I'll go to my desktop. It's called PyBullet Stream, and I think it's part 1. In here, I have nothing. Okay, it's this folder right here. So in Windows, you do py-m venv env. Okay, py-m venv. Up until here, it's the command that I have to use. Okay, env is the name that you'll give to your environment. I like to call it env always. It's the easiest way. So py-m venv env, run it. And takes just 2 seconds. Should take 2 seconds. There we go. And now, if I do ls, you can see there's an env folder there. Okay. For Mac and Linux users, if you have to do Python 3 -m venv env. This is for all Unix-based users, both Mac and Linux. Okay. Cool. Now, for Windows, you can do env scripts activate. Okay, again, if you're wondering how I'm typing that fast, I just type E and then tab, S and then tab, and A and then tab. Okay, so env scripts activate. Okay, and this should activate the environment. You can see an env, greenish env here. Okay, for Unix-based users, source env, I think it's bin activate, like this. Okay, same thing, but instead of scripts activate, it's bin activate, and you have to add a source before. Okay, this doesn't work in Windows. Shouldn't work in Windows. Yeah, there you go. It doesn't work. Okay, because source is not a recognized function. For Unix-based users, it is. Okay, cool. Nice. So, oh my bad. Oh my bad. Oh my bad. Oh my bad. No. Wait a minute. Nope. Nope. I don't want this. There we go. Cool. Okay. So, nice. So now we have our env. Okay. Oh, you're welcome. Nice. You're welcome, Tammy. You're welcome both. Nice. Okay. So we don't have PyBullet installed. Pip install PyBullet. Pip PyBullet. There we go. Like this. PyBullet. It takes just a teeny tiny bit. Okay. Before doing pip, make sure you have your env activated. Okay. It should take a couple of seconds. If it's not cached, in my case, it's cached. But if it's not cached, it's going to take a little bit more. So give it a chance, okay? But yeah, cool. So we have PyBullet here. Let's start to code, okay? Let's do intro to PyBullet.py. There we go. So let me just open my cheat sheet, which is my GitHub, okay? I haven't done anything in robotics, but here we are today. You know, it's not that I want to feel important, but robotics is maybe the best field of engineering. You know, it combines into everything: physics, software, AI. You know, math, like a bunch of math, a bunch of math, which we won't dive in today but it's a lot of math. But yeah, robotics is cool. Cool. Okay, so import PyBullet as P. It's usually what we do. Okay. Import time and import PyBullet data like this. Okay. Yeah, easy imports, nothing fancy as for now. Okay. Cool. So first things first, we need to load physics. Okay, we're creating a virtual world where we're trying to simulate the same as our real world. Okay, so load the physics server. Okay, I panicked and used Gemini CLI to help me with my pip issues. Oh, no worries. Maybe you have to do pip install -- upgrade pip, and then you have to do pip install PyBullet. Maybe it all depends also in your Python version. Mine is 14. Maybe, I don't know, just check your errors. Cool. Okay, so we do physics client equals p.connect like this, t.gui. Okay, like this. Yes, easy peasy. Cool. Okay, now we're going to use data from PyBullet that's already let's say preloaded for us. We have to use this thingy over here. Okay, so we have to set it up, and we do use additional robots plus plates. Okay, what's wrong with my typing? Okay, cool. P as for PyBullet. Okay, p.set additional search path. Okay, we do PyBullet data.get data path. Okay, and I'll remove this. Okay, once we start using robots, just for you to see what this means. Okay, but it basically says, hey, I want you to use also PyBullet data to use the robots that are already pre-created. Okay, cool, nice. So now we got our physics client, we got the additional search. Let's give it gravity. Okay, so can someone please tell me how, like, what's the speed, or I think it's the acceleration. No, it's the speed of gravity. Like, what's the number? Do y'all know? In the meantime, I'll just do set the gravity. Yep. Do y'all know the speed of gravity? Nope. Anyone? I'm pretty sure you do. Yeah, there you go. There you go. Cool. So 0, 0, 9.81. That's cool. Yep. So it's acceleration. It's squared. Nice. Cool. Yeah, I don't think so. $1 million. That could be cool, but it's 9.81. Okay. So if you see, we have 3 here. 0 for X, 0 for Y, 9.81 in Z. Okay. Close up. People are used to saying, okay, it looks like this. This is Y, which points up. X points to my left or right. And in 2D, that makes sense. But when you 3D this, you basically do this. Okay? So this Y, or actually you do this. So this Y becomes Z. So Z is always up. Okay? So Z, it's like this. Z, X, Y. Y points here, X points there, Z points up. Okay? So in my code, you can see Z is the one in charge of being up or down. Okay? Cool. Nice. So, actually it's -1. Minus 9.81. Okay? If I do it 9.8, it goes up. Okay? It should be down. Okay? Cool. Nice. So, let's load a world. Okay? A world that is just a plain world. Okay? Load a world. Plain ID equals p.load URDF, and then plain.URDF, like this. Okay? And you'll say, hey, Bully, I don't have plain.URDF. It's not in my, it's not here. Like, how will this find plain.URDF? Good question. Thanks to this line over here, we loaded PyBullet data, and plain.URDF lives in PyBullet data. Okay, so because of this, it will find it. Without this line, it won't. Okay? Cool. So now we have our plane, we have a world, we have physics, we have gravity. We're missing a robot. Okay? Let's just start to add a robot. Where you are, if you look around you, you have lots of things, okay? You are in a position in the universe, okay, where your coordinates are dependent on when you start to measure, but in the end, you have a position, okay? We need to give a position to the robot, okay? So give start position to the robot. Start position equals 0, 0, 1. Now, you'll say, hey, 0 in X, 0 in Y, which is the center of our plane. Why 1? Well, if we put 0, it's going to be in the middle of the plane. We just have to put it 1 up. So it's its feet or its wheels is on the plane and not its chest. Make sense? I'm starting to see the machine learning part. I'm just starting to get into machine learning. Yeah, machine learning part is going to be part 2. Okay, let's just understand first how PyBullet works, and then we start to add the machine learning part. But yeah, by the way, stay. Like, don't leave. You'll get to see robots. Okay. Cool. Awesome. Makes sense to Tammy. Cool. So we'll get into something interesting. Start orientation. From Euler to quaternions. Okay, cool. So we get the start orientation equals p.get orientation from get what? Wait a minute. Get quaternion from Euler. My bad. It's a weird name. Get quaternion from Euler. There we go. And now 0, 0, 0. Cool. Okay, so what the heck? Like what's this? Get quaternion from Euler. Great question. So back to my slides. We have Euler angles, which Euler angles are used with the, okay, so the coordinates that I shared with you. Z is always pointing up. Z is always yaw. Okay, when you're yawing, you're doing this. Okay, close up time. There we go, you're doing this. Okay, if you're rolling, you're doing this side over here, which is like this. If you're pitching on this side over here, which is like this. Make sense? So check this out. Roll, it's yaw in the Z, pitch in the Y, roll in X. Okay? These are called Euler angles. Okay? I won't get into the gimbal lock, but yeah, you use roll, pitch, and yaw for your robots. Okay? Sometimes when you're simulating, like in this case, you need to get quaternions. Quaternions are the mathematical way of PyBullet representing orientation with 4 numbers. Okay, so it's X, Y, Z, and then rotation. Okay, cool. It's just going from 3 to 4. Okay, PyBullet loves it that way. Okay, cool. So I won't get into the math. Okay, I will avoid math right now. It's just not for a 2-hour stream. Okay, cool. So we get the quaternions of 0, 0, 0, roll, pitch, and yaw. Okay, it should give us a quaternion of 0, 0, 0, and maybe something else. Okay, cool. Now, oh great, GitHub crashed on my iPad. Cool. Where is it? Let's see. Where is my code? Wait a minute. What? Repositories? Inbox. Wait, what? Wait a minute. What? Oh, there we go. Repositories. Wait a minute. I'm sorry. My iPad just crashed. Code and then APIs 2026. Autonomous Car Park 1. Okay, cool. There we go. Nice. So we have our orientation. Okay. Now, remember I said robots are boxes with cool skins, and the boxes represent the hitboxes. Yep, that's what we're going to do. Okay, load the URDF of the robot. Cool. So box ID equals p.load URDF. Yeah, and then let's call R2D2. Okay. .urdf. Okay, R2D2.urdf also lives in PyBullet data. Okay, no need to create it. Now we're spawning R2D2. Where? Start position, which is 0, 0, 1, and start orientation. Okay, because a robot can have. Let me just get something. There we go. This little notebook you see here, it can be like this, like this, like this, like this, like this, like this. It has an infinite amount of orientations, and we'll choose 0, 0, 0 orientation, which is facing in front. Okay, cool. Nice. Now, killer switch, okay? For our computer not to overload or getting stuck on a thread and never getting out. Use loop to control system, okay? For underscore in range, is it 10,000? 10,000, yep. Cool. P dot step, sorry. Have the physics sim step. Okay, so whenever we're inside of our loop, we need to run one step our physics engine. Okay, so one step it recalculates if it's up, it should go down. Hence, like because of gravity, it should go down, so on and so forth. Okay, so let's have that physics running. P dot step simulation like this, and then something interesting. Okay, depending on your CPU, you might have a very, very, very fast simulation, or a very, 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 not a very, very, but somewhat slow simulation. Okay, PyBullet is set to run at 240 hertz, which is 1/240 seconds. Okay, now we need to reverse that so it's once every second, so it looks natural. Okay, so make the time natural like this. So time to sleep 1/240. Okay, there you go. Yep. In case our computer gets stuck in a thread because it tried to load a robot and whatever, and we can't do anything, we'll just wait a little bit for this loop to end, and everything should just collapse. Okay. Okay. Yeah. So in this case, it's an arbitrary number. It gives us enough time to see and play a little bit before it collapses. Okay. It's just the failsafe in case a computer gets stuck in a thread loading a robot or something. This keeps counting. If we cannot close the thread, this will close it. Okay. Cool. So that's that, and then yeah, let's not do that. Let's do p.disconnect like this. Okay, so in the end, when everything ends, we disconnect. Okay, all good. If you have any questions, just let me know in the chat. Let's just run this. Let me just do it like this. Intro to PyBullet.py. Yeah, exactly. Thanks, Tammy. Yes. It's an arbitrary number of frames. Yeah. It's not seconds, so careful. Cool. 3, 2, 1. And you don't see it, but I do. You can see that. Here's R2D2. I can just do this, toss it over. It should fall down. Up. It should fall down. There we go. See that? That's a robot. All good? Works for everyone? Woo! Okay, I'll try to. Hey, stop. There we go. Yes, it works. Awesome, Tammy. Cool. And now you can see we don't have anything, right? Like this robot is just a bunch of boxes that, doesn't do anything. It's just a bunch of boxes with a. There we go. Failsafe. Okay, in case. Like I ran out of time, okay? In case your computer gets stuck in a thread, this will kill it, okay? It didn't get stuck, but, it's just a failsafe for anyone who gets in trouble, okay? Nothing in particular. You can see it has a little arm here, and it doesn't do anything. But we can do lots of things with it, okay? Toss it out. Cool. Sorry. Woo! Yeah, that's not good. What? What? Well, that's a bug. Okay. Yeah, gravity stopped working. Okay, cool. So this is the most basic thing of PyBullet. Okay, first understanding PyBullet, infinite spin. Yep, without any gravity. Okay, awesome. Cool. Now, if you don't have any questions, let's just go to something more interesting. Let's just do I don't know, robot class.py. Okay, cool. Now, I love to rewrite stuff. So we remember what we wrote, okay? So this is the autonomous car parts 1_2 in my GitHub, okay? And it's a lot of code, okay? So bear with me. Cool. So import PyBullet. SP, we know it already. Import time. Import PyBullet data. And import math. Okay, math is already included in Python. You don't have to pip install it, okay? Cool. All 4 libraries that we need. Let's start with a class. Class define simulation, okay? Maybe we'll use this class for Tuesday when we train the car, okay? We'll use the functions inside of the class to train the robot, okay? Cool. Now, if you're unfamiliar with Python, please let me know so I can explain more what class means, what this function means, okay? Just let me know, okay? No worries at all. Cool. So we're going to create a constructor inside of course self, and then and not track points for now. Okay, like this. Yeah, cool. So we did it before. We'll do it again. Oh, please explain. What do you want me to explain, Maggie? Load the physics server. Ah, Yonko. Okay. Cool. So a class. Okay. Let's see. Where do I have something interesting here? This is an object. Oh, let's just do interesting close up, okay? Quickly. This is an object, okay? A simple pen. Yep. You have all of these around the world. Everyone uses them, yet every single one is unique, right? Like the one that I have is the one that Tammy doesn't have because I have it, not Tammy. Okay? Yep. But it still is an object. Okay, it looks the same as Tammy's, but it's not Tammy's. This is an object. Objects come from classes. Classes in Python. Okay? So a class is like a molding or like a mold or a machine that creates objects. Yep. You need functions inside of your class to create cap, ink, and plastic. Yeah. So we do functions inside of the class, which is your machine, to create a pen. Make sense? So we do a class full of functions to create robots, to start the robots, start the simulation, start everything. Does that make sense? Yeah, exactly. It's like a class in C#. Yep. Cool. I hope that helps. Now, if you ask what is a class, I'm pretty sure you're not familiar with the constructor. Init is a function that runs, or it's called a constructor. It runs when this class is called. Okay, so when you're creating an object, this gets run, and it's the first thing that runs automatically in your code. Okay, yeah, good. So we can do things here like a load cell, for example, cell.physics client equals p.connect p.gui. Okay, same thing as we did before. Here you can see it's the same code, but I know that this one will run at the moment where I create an object using this class. Does that make sense, Yonko? Yes? I hope it helps. But yeah, that's what it does. Just let me know if you have any other questions. Awesome, cool, nice. So we have the server, same as before. Use data to call other objects like robots. Same thing. P.set additional search path, and then PyBullet data.get data path like this. Okay, same thing as before. We're saying, hey, I want to use PyBullet data. Okay, cool. Now, Remember, we have our physics, but we need to set the gravity. So P dot set gravity, and then without an R. And then what extension do I need to be able to use Python on PS? I don't think you need extensions. You just need to connect VS to your Python path. So I don't have many extensions here, but not Python extensions though. For example, I have .NET, Andromeda. No. Mine? Where are mine? Installed, yeah. So I don't have any Python extensions other than C and C++ ones because they're not native or Javas. But other than that, you don't need any extensions for Python. Visual Studio Code just does it automatically, okay? You just need to connect Visual Studio with Python, okay? Cool, so set gravity, it was 0, oh, not a list, 0 minus 9.81. Okay, same thing as before. Next one is self, that's start position equals 0, 1. Remember, we add a 1 because if not, the robot will be kind of embedded in the floor. So we don't want that. We want it over the floor. Okay. Cool. Cool. Awesome. So, nice. We do the same thing as get starting position. Okay. And now self dot start. Oh, actually, get the starting orientation as before. Okay, the weird quaternion other thing. That's what we need. Self dot start orientation equals p dot get quaternion. Yeah, there you go. From Euler. And again, it's starting position. Okay. So we got a quaternion from the orientation here. We load the plane. Okay, so self that plane ID equals p dot load URDF, and then plane dot URDF. Okay, same thing as before. Okay, same thing, just inside of a constructor. Okay, cool. Now, we won't do that for now, and not that. Okay, cool. So for now, we'll be adding some stuff later. Okay, what do we have? 0, 0, 0, 0, 0, 1. Ah, okay. So 0, 0, 1 is for your position. Okay, so position is where you're at. Orientation is where you're looking at. Okay, so for example, it can be the same position, but my orientation, yep, is just changing all the time. Okay, but I'm in the same position. I'm not moving. I'm just turning, right? So same thing here. If the starting position is 0, 0, 0, then I'll have my, this is the plane, I'll have my robot stuck in the plane because it's in the middle. Okay. If I do 0, 0, 1 here, instead of looking this way, it'll be looking like that way. It's like, this is the starting position. Okay. The orientation and position. Okay. Yeah, sure. Awesome. Okay, cool. Nice. So let's do a function called spawn robot. Okay. Okay, where it gets self and URDF. Okay. Always, please, please, please keep your comments as commenty as possible so that whenever you come back to your functions, both in production and in personal projects, you can know what you did. People change in 2 months, or your coding style change in 2 months. You know, just do yourself a favor and, you know, just explain it to your future self what you're doing. Okay, it happens to me all the time. I'm like, what was I doing? What was I thinking? So yeah, so let's write here function that spawns URDF robots with when called. Okay, like this. Nice. So it's just a one-liner. Load the robot as a box. Again, URDFs. Yep, URDFs are a bunch of boxes put together to mimic the hitbox of a robot. Okay. Tammy says, thank you, Bully. I need to put doc strings in. Yeah. If you don't, and you go back to your code, it's just a mess. Because your line of thought is not the same now that in 2 months. You just forgot what you were doing, and it's just a pain to come back and read the whole code. Cool. Okay, so self.boxid equals p.load URDF. And then what will we be loading? This URDF right here. Self.start position. Self.start orientation. Okay, like this. Easy. Okay, a function that just spawns a robot, puts it there, quits. Okay, nothing too fancy. Okay, nice. So now what's the next one? Okay, run simulation. Okay, cool. So let's do def run simulation like this. It has to have the self inside. Same thing, a doc string saying or a comment saying function that runs the simulation. A period. It doesn't do any more. It just gets everything, puts it in one place, and runs it. Okay. So for same thing. Okay. Our fail safe. So for I in range 10,000. Okay, we'll just put an underscore for people who are starting with Python, and you see underscores for Python people like this. Calling a variable an underscore is a variable that we won't use. Okay, so it's just like an underscore because we won't use it and we don't want to waste variable names. Okay, cool. So for I in range 10,000. Same thing. Do the step of the physics server. Okay, so self did step simulator like this. Simulation, sorry, like this. Cool. And then same thing. Reduce the 240 hertz. Okay, so time.sleep 1 over 240 like this. Okay, nice. In the end, after this for loop, disconnect the server. P.disconnect like this. Okay, so we just did the same thing inside of a class. Okay, now for people who are just writing their first class, let's just run this, right? Like same thing, it's robot class. So I'll do robot class. I said let's just do robot. It doesn't do anything, right? Like I can do it 4 or 5 times. It doesn't do anything. Why is it not doing anything? Yep, for people who it's the first time calling a class, we actually haven't called a class. It's defined, but I've never said, hey, Python, I want you to create a robot. Yep, the code is there. I never called it before. Okay. Yeah, you're right. So to do that, we do if dunder main, dunder name. Dunder means double underscore, double equals dunder main like this. What does this mean? This means, hey, is this being called by main, which is moi? Okay, main is this. This is main. Okay. When something is not called by main, it's because this might call this. Okay, so you can call a class from another Python script, and that's not main. Okay, yep, makes sense. Yes, yes, a little bit. Cool. So if we're calling it, if person is calling it, then create sim object simulator equals, and it's called define simulation. Okay, define simulation like this. See, it auto greens it for us. Thank you, Billy. Does that bottom code only execute code from the above? Do you mean this one? Yeah, it executes codes like inside of your script, if and only if you're calling it yourself from the terminal. If you do, for example, if I do here import robot class like this, when I use it inside of this, it's not main anymore. It's being used by intro to PyBullet. Make sense? So it's not me calling it directly, it's intro to PyBullet calling robot class. Make sense? So this doesn't work. If I'm calling this from my terminal, this works. Okay? It's mainly for debugging purposes. Cool. Okay, so simulator, and then we do spawn a robot like this. So simulator dot, which means from the simulator object, I want to access spawn robot. Okay, let's just do it. And then the URDF is going to be called r2.urdf. And then run the simulator. Okay, so simulator dot run. Simulator dot run simulation like this. Okay, this function right here. All good. We have a class that does exactly the same thing as we had here, but in a more controlled way, so we can add a machine learning to it. Okay, go. So let's go back here. 3, 2, 1. What? Okay. When you get this, as I always say, please do not run away from errors. Don't go and copy paste the whole thing into ChatGPT. Try to read it. Okay, let's read it together. It says, error argument 1 must be a string and not a function. Okay. And which line? It says line 13. Okay. Ah, see that? There we go. I missed calling the function. Okay. Cool. Careful there. Okay. Nice. 3, 2, 1. There. What? Again? What now? Step simulaton. Missed an I there. Tammy, keep count. It's 2 now, right? Step simulaton in line 39. Simulation. Good. There we go. Okay. Will I get a third error? Yep, there we go. Always. Step simulate. What? Run simulation. Step simulation. What when you say when errors say missing command line 3, but you see yeah. Okay. Run simulation. What did I write? Run simulate. Isn't this? Step simulation. Did I just get it wrong? What? What's the error? What the heck? Nope, no thank you. Define simulation has no attribute step simulation. What? It's this one. I'm just stupid. I'm sorry. It's P. Yeah, the function exactly. The function doesn't exist because I was trying to call it from this class. But this class doesn't have that. It's PyBullet. Yeah, and I said instead of P, I put self. Self means this class. Okay, and yeah, you're right, Yonko. Instead of doing self, it's P. Okay, my bad, my mistake. Yep, it's for as for now, Tammy. There we go. Now it works. Okay, it looks exactly the same. It does exactly the same. If I throw it away, it does the same. Should be down now. There we go. Oh, from here. Cool. All good, right? Nothing fancy right now. Okay. Cool. Now let's run it again and see what are we missing. So we already have R2D2. Let me just kind of rotate it here with my mouse. There we go. Cool. So what's R2D2 missing? Okay, what? It doesn't do anything. It's a bunch of boxes, right? Like, it doesn't do much. And robots, as humans or animals, see, right? They have sensors. They have either a camera or a lidar. Okay, so let's add sensors to a robot. Okay, in the end, our robot has to be able to see in front of it for it to drive. Okay, and basically make a decision. Okay, now the robot that we're going to use is called race car. I think it's called race car. Was it race car? Nope, it's not called race car. Darn, I forgot. Race car, URDF, PyBullet. What's the name? It's race car, really? Race car? No, it's not race car. I remember it was. Let's see. How to use race car in. It was like a F1 race car or something like that. Come on, AI. Yeah. Oh, there we go. Race car / race car URDF. Okay. There we go. Maybe. Will that work? Yep, there we go. You can see it now. This is the card that we're going to use. Okay, you can see even it has this on top, and this is an MIT car, okay? This is a lidar, okay? And I'll explain what a lidar is, but we're going to mount our lidar here to mimic a real robot, okay? Close this. There we go. Cool. So back to my slides now. Last slide is what is a lidar? Okay, a lidar is a light detection and ranging. Okay, what is this? Okay, why don't we use a camera? Okay, and we'll see why a camera is not a good idea. But this thing is like a disc. It's is Tesla using PyBullet? I don't know, maybe. What I do know is that Tesla uses cameras, not lidars, and Waymo, which is your robo-taxis from Google, they use lidars. Okay, that's why they have the big thing on top of the car, and Tesla doesn't. Tesla uses a camera. Okay, it's a different type of technology, but yeah, both of them have their pros and cons. Okay, cool, but this is how a lidar looks, right? Like you see every single one of them is a point, right? So this thing is like a disc. It turns multiple turns by second, and it shoots beams of light everywhere. Okay, and yeah, exactly. Computer vision versus lidar. Yep. And when the light hits back, you can measure the distance of the objects and kind of draw like a dot map of how your environment works. Okay, you can see here in this case, like in this example, this is not accurate actually, but things that are closer to you should be red. Things that are way farther than you is blue. Okay, that's what we're trying to program. Okay, we're going to add a lidar to our robots and measure And when we get to part 2, which is the machine learning part, we'll actually get to use the measurements to make decisions. Sound good? All good? Okay, nice. So, get rid of this. Let's go to our code. And, yep, should be good. Let's add, just right here, def place sensors, okay? Self, because we're inside of the class. And in this case, we're going to add a sensor. Okay? Cool. And so, always your comments. A function that, let's call it activates the sensor. Over robot, we have camera and LiDAR. Okay, these are the two options that we'll have now. Okay, cool. And so for both camera and LiDAR, we need to get position, orientation, and get the rotation matrix, which I'm going to quickly explain in a second. Okay, so get the position and orientation of the camera, the sensor. Basically, where are we going to put it? Okay, this part right here, it's basically where we're going to put the sensor. So, position with S, orientation equals p dot get base position and orientation of the box ID. Okay, let's just take a let's just take a break and actually read this. Get base position and orientation of what? Of self.box ID, which is my robot that I should have spawned before calling play sensors. Okay, so we have a robot. We say, hey, where is my robot and where is it looking at? When we get that information, we can put our sensor on top of the robot. Sound good? Nice. Okay. So we get the rotation matrix. Okay. Now we need the rotation matrix, and we'll get it from here. Rot matrix equals p.get matrix from quaternion. Okay. So we get the orientation as a rotation matrix. Okay. Cool. Now we got those two things. If sensor double equals, let's start with the camera. Okay. What happens if we are working with the camera? Okay. Well, let's pass now. Okay. Let's do lf sensor double equals LiDAR pass else print. Let's do sensor not recognized, like this. Okay, yeah, give me a second, Mr. Draw. So I'm going to remove the passes just now. But in case we put something to this function that's not camera or LiDAR, it just returns an error. Okay, that adds robustness to your code. Okay, cool. Mr. Draw says, what is the P object? Okay, P is for PyBullet. Yep. Import PyBullet as P. It gets you every PyBullet function there is. Okay, cool. Awesome. So, starting with camera. Okay, cool. So, for a camera, we need to see forward. Okay, because we're simulating everything. We need to know what forward is. Okay, This rotation matrix has forward, or like in front, back, and around. Okay, and it has 9 parameters to it. Parameters 0, 3, and 6 are the ones that point in front. Okay, that's all you need to know for now. Okay, cool. So we'll do forward equals a list of rotation matrix in 0, which is one of the forward, rotation matrix in 3, and rotation matrix in 6. Okay, these 3 points are pointing forward. Okay, cool. Now, the camera eye is going to be X, its position 0, Y, its position 1, and Z is position 2. I'm sorry, 2 plus 0.3. Okay, this number is the height of the robot. Okay, now this is for R2D2. Okay, let's actually look for it. Height of race car to RDF in PyBullet. Let's see, 0.05. Okay, so in this case, we need 0.05, like this. So it's mounted on top of the little cylinder that you saw there. That's what it should be. Okay, cool. Now, camera target equals a list of lists. No, actually, it's just a list. Position 0 plus forward 0. Same thing for position 1 and position 2. Oh, my bad. 1 and 1. And for Z, position 2 plus 0.2. Okay, so this is just the height of the camera. Okay, again, you can simulate a very big camera, a small camera. This is what I found to be, usual, a camera. Okay, good, nice. So that's our camera parameters. Okay, there's not like a hey, get me camera object and I want you to give me whatever. No, you have to simulate everything. Okay, that gives you power. You can design whatever you want based on what you have. Okay, cool. So view matrix, we need a view matrix. Okay, p.compute view matrix. Okay, inside of this function, we're going to put camera eye position equals, we have it here, camera eye. We have camera target. Oh, my bad. Camera, it's a camel case. Target position. Tell me you write C#, C++, and Java without telling me you write it. People who use camel case. If people use kebab case, it's more of a Python thingy. Okay. Camera. By the way, people who didn't understand, kebab case is this, and camel case is like this. Okay, so instead of saying like this, I'm saying it like this. Kebab case, camel case. Okay, yeah, because this looks like a kebab. Okay, that's, I don't know, that's how I was taught. Okay, cool, awesome. So camera target, and then camera up vector equals 0, 0, 0, 1. There we go. Okay, that's for the compute matrix, which makes the camera, gives the camera the position, the target, and the height. Okay, cool. So now, projection matrix equals p.compute projection matrix FOV. Okay. In here, FOV, these are just parameters of the camera, 16. Aspect, I'll talk about aspect in a second, 320. I said 320 over 240. Near value 0.1 works, and the far value equals 100. Okay, so these are like how far will it see, how close will it see, the aspect, which is 320 by 240 pixels. Okay, and the FOV of 60. Okay, cool. Now, last function of the camera, underscore. Why? Because I want to use it. Okay, I'm just calling the function. Okay. It's 1, 2, 3, 4. I'll actually won't unpack it. I'll just do underscore equals. It's okay. He does get camera image like this. Okay. Inside, I'll get the width of the camera, which is 320. What we said, aspect of 320. Height of 240. What we said. We need view matrix equals. I'm sorry. There we go. That's readable. View matrix is my view matrix. And projection matrix equals my projection matrix. Yep, all good. Yes. I think we'll need to unpack them because it returns 5 things. So let's just unpack it with 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. So it returns 5 things because they're not packed into a single list. It'll return an error if I just do 1 underscore because I'm not using it. I'm just using an underscore. Okay. All good. Thanks, Sammy. Nice. Cool. Any questions? I'll give you 2, maybe 1 minute for questions while I drink some water. It's pretty windy outside, by the way. It's been raining so bad. Yeah. Will it rain? I don't know. Cool. Okay, no questions. Let's see what this does. Okay, which, by the way, place sensors, and I'll do. It should be in run simulation. Yep. There we go. It should be here. Place the sensor. Self that place sensors, and the sensor equals camera. Okay. 3, 2, 1. What? Camera eye position, function missing require argument, camera eye position. What? Camera eye careful. I just wrote position. Not position, but position. Careful with position. Okay, 53. See, don't run away from errors. You get to read it's a skill reading errors. Don't go to ChatGPT, copy paste your errors. Try to debug it yourself. Okay. Eye position. There we go. Position. Okay. Cool. There we go. Nice. I'll just get rid of these 2. You can see the camera is there. It's not the height that we want. Maybe a little bit up. I'm trying to. There we go. This is not bad, actually. Whee! See that? It's floating. It's floating. Should be down now. Did I add gravity? Yeah. What the heck? Where's the car? What? Am I that strong? Yeah. Was that me, or was that like a Hulk toss? Can I grab it? Come here, you. Bad thing about PyBullet is there's not a pan option. We have to program it. Okay. But yeah, there's our car. It comes here, you. There we go. Blah, 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 blah. There we go. Cool. Awesome. So this is a camera. Maybe we should put it a little bit up. Okay. Let's try that. Let's see. Maybe that 0.05 wasn't accurate at all. This one right here. Maybe 0.2 as I had it before. Maybe. I don't know. Would that work? Okay. Okay, that works. I think that's almost, yeah, that's good. Okay, cool. Now, it works. It's not bugging as I was hoping it would bug. So let's get back to, instead of race car, I'll just do R2D2. Okay. Why is that? There's a bug that I want to show you. There we go. See that? Do you see that? It's really slow. See that? I just tossed it away, and it's kind of like in the moon, right? Like, check that out. Okay. Yeah, can you see that? It's really slow. It's not even trying anymore. See that? Why is that? Because when you're simulating and in real life, when you have a camera, cameras are really, 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 let's call it resource expensive. Okay? Reading images, parsing them, it's actually very, very heavy. So what we usually do when you have a camera, and that's why if you can use something that's not a camera or a very low aspect camera, it's better. Okay? No, it's not because of time slip. That's something that usually people think. This time slip here is just telling you, hey, PyBullet, I want you to go to 1 second. Like 1 human second. Okay? This, being a camera, is very expensive. What we have to do when we use cameras with robots, especially because your hardware is limited and your battery, which is your most precious thing, gets drained really fast. What we'll do, instead of using underscore here, let's call it I. Okay? So for I, or actually if I over 5, or like the remainder over 5 double equals 0, then I want you to place the sensor and read it. Okay, do you get what I'm doing? Chat. Each 5 frames, I'm going to read the sensor. Okay, it's not going to disappear. It's just going to take 5 frames for me to read it. Okay, check this out. Okay, now it's kind of working. See that? It's maybe a little bit slow, but not that slow. See that? I just tossed it away. It should come back now. It's kind of more accurate, right? Maybe if we do over 10. See that? Okay. I think that's better. Yep, that's better. Yep. Now it's good. Whee! Now you're not losing a lot of information if you're skipping 10 frames, depending on the speed of your let's call it like your cycles. But you see that? Now that I'm skipping, I'm just like, I'm not losing any information. I'm just not reading every single second or millisecond, reloading the camera. I'm just doing it. I'm just doing it every single 10 frames. Yeah, and this makes it smoother. Okay, so that's the problem always with cameras. It's that they're really expensive because you need lots of resources to measure the camera. Okay, to read the frames, to basically, if you use computer vision, you're going to have to put filters and neural networks for you to decide, and that lives in one thread. The other thread is your robot, so on. Okay, yeah. That's the bad thing about, let's call it robotics or hardware, is that you're working with real life things, and you depend on your battery and your processing power. Okay, and if you don't do this, then your drone doesn't read the messages from your computer, so on. Okay, it happened to me. Yes. Cool. Okay, so that's for the camera. Okay, let's go to and install a lidar. Okay. Cool. So a lidar is a little bit similar, more math to simulate, but let's do it together. Okay, we have 30 minutes. So we have the same forward equals the rotation matrix in 0. Remember, forward is 0, 3, and 6. Okay. Rotation matrix in 3 and rotation matrix in 6. Okay, that's our forward. Cool. Okay, now we're going to normalize forward for this one. It means instead of well, in this case it's squaring it and then do square root, so we get a vector. Okay, so normalize forward. Okay, so norm equals math dot square root. Okay, and forward in 0 squared. I said it was going to be more mathy, plus forward in 1 squared plus forward in 2 squared. Okay, we're going to get a vector, which is a normalized vector. It's just one number that looks forward to all 3 forwards. Okay, so it gets the mean of the forwards. Okay, cool, nice. So now our real forward is going to be a list of f over norm. Yep, for f in forward. Okay, that's it. Cool, nice. Now, no more math. Let's go to configure the lidar. Okay. Cool. So, num rays is going to be the amount of rays that we're going to shoot, or the beams that we're going to shoot. Okay. So, it's going to be 15. The ray length equals 10. I'm sorry, I think I unzoomed. Speed angle equals math dot pi over 2, and ray from equals this. I'm explaining this in a second. Ray 2 equals this. Cool. Okay, so 15 rays. Okay, so beams are going to be shot 10 meters of length. Okay, the angle, the speed angle is going to be 90 degrees. Okay, so it's math.pi, which is 180 over 2. From and to is going to be the starting point and the ending points that we're going to store and then process to see if there was something there. Okay, cool. So generate the rotating let's go shape. Okay, so again, we are going to simulate everything, so we need to simulate the rotation too. For I in range num rays, like this, angle equals minus spread angle. Oh, my bad. It's not speed, spread. There we go. Spread angle over 2, which is 45, plus spread angle times I over num raised minus 1. Okay, that's the angle of each num ray. Okay, cool. Now, the more num rays, the smaller the angle. The less num rays, the bigger the angle. Okay, cool. So, rotate. Forward vector in XY plane. Okay, so what are we going to do? Close up again. This is my forward. Okay, yep, when I move, my forward should move with me. Okay, the robot's forward is this. The LiDAR's forward will be doing this, or basically this. Yes, moving, basically turning. Okay, but the robot is still looking forward. So we need to keep that forward of the robot intact, and the LiDAR is just doing this. Yep. So we need to, based on the angles, change the forward to here, 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 all the way up to a full turn, and do the same thing all over again. Okay. So this will maybe look clearer in code. XY plane. In X, we'll do forward in 0 times math the cosine, always cosine for X, angle minus forward in 1 times math the always sine in Y. Okay, like this. Okay, that's the difference. Like, yeah, the difference, or the movement in X and the movement in Y is forward in 0 times math the cosine angle plus forward in 1 times math dot, again, for Y it's sine angle, like this. Okay, so we have the moving X and the moving Y. Okay, cool. Now, start equals a list of position 0, position in 1, and position in 2, plus 0.2 seems to be a good height, so let's keep it at 0.2 for now. Cool. And end equals a list like the camera, position in 0, plus the movement in X times the ray length. Is it making sense now? Let's maybe grab some paint here. There we go. Paint, paint, paint. There we go. Cool. Is it? Can you see this shape here? Is there a shape here? Like a zero, like an oval, oval, oval? That's weird. That's the first time I've ever seen that before. Yeah, see that? It's like an octopus? I don't know. Looks weird. Okay, cool. So we have the car. Okay, this is the car. We have LiDAR is here. This is the LiDAR. Okay. This is the car's forward. And the LiDAR's forward is going to do this, 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 like this. See that? It's going to do that 15 times. Okay. It rotates, so it maybe goes like this. This is your ray length. Yeah, see that? If it would be 20, it would be here, but it's 15, so it's here. Okay? And then if we say, hey, I just moved an angle, so my ray length times the angle plus the position, which is this position over here. That will give me this point, this point, this point, this point, this point, this, and this. Does that make sense now? I'm just shooting out beams. I'm saying if I'm here, the beam is 15 meters long. It should be there. Let's, based on the angle of my turn, it should be there. If it's not, then let me calculate what's in front of me. Yep, a little bit better. I hope it makes sense, okay? Cool. So, same thing for position in 1, which is your y plus dy times your ray length. Yeah, because if the car moves in the y position, then it should, okay? And, oh, thank you, Tammy. Tammy understands. Okay, and position in 2, which is the z position, plus 0.2. We're turning in z, okay? But we're not looking up. We're looking in front and in the sides, okay? Cool. So, nice. Let's do this. Ray from the append start. Ray to the append end, like this. Okay, so we append the start and the end. And based on all of the objects that we have in our world, we'll see if we have something in front of us or not. Cool. Okay, so a little bit more math and we're over, I promise, okay? Now, cast the rays. Results equal p dot ray test batch. Inside of this function, we're going to do ray form from and ray to. Okay, so we give this ray test batch the from and the to. This will take care of the calculation. Okay, cool. Now, store. Maybe we won't use the distances now. For part 2, we need the distances to see what's in front of us. Okay, so self the distances, because I want this to be accessible throughout the class, equals an empty list. Okay, cool. For I are in enumerate. Enumerate gives you the number and the index. I'm sorry, the index and the value of each thing inside of a list. Okay, so enumerate results. So for every result that we have, give me its position from 0 to its length, and R, which is the result. Okay, we can do even like this result. Okay, so it's easier to understand. Hit fraction equals R result into. Okay. Cool. So if we get 0 if hit immediately, 1 for no hit. See? So we go from 0 to 1. 0 is, hey, if I got a 0 value, it means there was something right in front of me, right here. If I got a 1, it means there was nothing in front of me. Okay? Cool. Okay. Nothing, like this. Cool. Now, distance equals hit fraction times ray length. Okay, so the ray length times from 0 to 1 or from 0 to 100%. Okay, that's the distance. Okay, and then self the distances that append, which is my distances, I will append list. Yeah, so I remember position and the distance of the ray, and I can say, hey, if I turn a little bit left, I'll find something, but in front of me, there's nothing. Okay, cool. So, hit position equals result in 3. Okay, and then if hit fraction is less than 1, then we hit something, okay? And then, shouldn't it be results on line 0.7? No, because, yeah, okay, that's a good question. So from the results, I'm getting enumerate gives me, so let's do it here, okay? If I have, for example, x equals 1, let's do A, B, C, D, okay, like this. If I do enumerate, this would be for the first iteration, I would be equal 0, and let's call it, I don't know, R is going to be equal A. Okay, for the second iteration, I is going to be 1, this is going to be B. The third one is going to be 2, C. Yeah, so you're iterating through each and every single one of them. Enumerate gives you your position in the iteration and the value. In this case, instead of results, the whole thing, it's giving me each result of results. Okay, so in line 107, I'm getting from each beam, or from the 15 beams, it gave me 15 results. From those results, I'm getting each beam's result and saying, hey, did I, with beam number 5, did I hit something? Yes, no, maybe. And this is why I'm using a result instead of saying results, because I'm going beam by beam. Does that make sense? Better? Yeah, I hope so. Okay, just let me know if that wasn't as easy as it. Yeah, okay, cool. Nice. So if we hit something, p dot add user debug line, and then ray from in I. Okay, so we're using the I here. Hit position. Okay, we're going to color this red. So if it's RGB, red, green, and blue, okay, red is going to be the most red. Nothing in green, nothing in blue, so we have a very bloody red. Okay, that means, hey, you're hitting something. Okay, and then lifetime 0.1 seconds. Okay, so we don't have a lot of rays that are just unused there. Okay, cool. Now, what if we didn't hit something? No hit. So p dot add user debug line ray from. So we're drawing the rays, okay, to ray 2. Yep. So it's not my hitting position. because I didn't hit anything. Okay, so I'm saying, hey, from the ray, from the start of the ray all the way up to the end, it should be what? If it's RGB, 0 for red, 1 for green, 0 for blue. Okay, same thing. Lifetime should be equal to 0.1. Okay, so we don't have a bunch of green rays just lying around. Okay, cool. That should be it. Let's just change instead of camera. We don't need this anymore. This is just for the camera. We need lighter. Y'all ready? Tammy, start counting the errors, please. 0. Yep, there you go. Careful, debug line with just a capital D, not capital E. Darn. There we go. Add user debug line. Okay, it should be good. 1. Get a 2? No, we didn't get a 2. Okay, we don't see anything. What happens if we move the robot? Ooh. See that? Y'all see that? No, that's laggy. That's not good. Maybe we should add... Yeah, maybe we should add a little bit of a... Yeah. Okay. Never mind. Oh, God. Yep. Okay. Let's just add a little bit of breathing between each light beam. So if I over 5, let's do the same thing as the camera. Maybe it worked for me before yesterday, so shouldn't be laggy. Okay, that's less laggy. Okay, yep, that's good. See that? Do you see the green lines? Yep. Because we're just looking at it like this. If we look at it from the top, you can see that the lighter is actually spinning. Yep. Oh, come on. Okay. Yeah. There you go. Yeah. 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 Come on. Yep. You can see that when we hit the floor, it looks red. Yeah. Just go. Yeah. You know what? Just go. And now it's spinning again. Oh God. Oh. Okay. Now it stopped spinning. Okay. So now we have a lighter. Okay. I won't run it again because my computer's fan. I don't know if you can hear them. It's really loud. I have StreamYard open. I have this open. So it works now. I'll run it again just once. Yeah, it's cool. Now this is going to be what we use tomorrow. No, not tomorrow. The next part for the autonomous part, which is these lights are going to be the ones that dictate whether we see something or not. Okay, I'll just close it now. Cool. Okay, so yeah, should I do this? Maybe we don't have time. Okay, so I'll just copy paste the whole code because I don't have time, and I'll explain it. Okay, should be number 2. And should be this one. Create walls, okay? Cool. So maybe before run simulation should be good. Okay, let's see. Cool. So we create walls. We can create walls, okay? The walls are going to be the ones that, or we're going to use walls to draw our track. Okay, we have a thickness of a wall and the height. Okay, like that. It's pretty intuitive. You know, we can make it very thick or very high. Okay, cool. We're going to draw all of the points. Yep. What? Oh yeah. Okay. Yeah. So we need to add something called add track points. So these are going to be the coordinates of our track. So we draw it. Okay. So softed track points. Okay. Equals this. So for now, we're going to accept as our first argument in init track points. Okay, so whenever we call this function right here, or actually the class, track points is going to be, let's just copy paste this, 0, 10, 10, and 0. Okay, cool, like this. Okay, cool. Now, we don't want R2D2. We want race car / race car. There you go. Now, what does this function do? It gets from all of the track points. We get track point number 1, track point number 2, which is X and Y. We get the distance. We get the length using square roots and doing the squares of both. So you square both of them, you sum them, and then you square root them. You get the length. Okay. Now, if we don't have length, we'll just return because it's a no wall. We get the center, CX and CY. Okay. We get the yaw. Okay, so the orientation of the wall. Get the quaternion to get the orientation. There we go, the yaw. The half extents. Okay, so in the end, it's going to be 2 walls, and in the middle is going to be the track. Okay. We have to have collision. We have to have visual, and multi-body means I want to create multiple walls. Okay. Cool. The way we'll use this is, we don't need this. Cool. So we have to update I, by the way. We updated +2 because we need 2 points for each wall. Okay, because point 1, point 2, draw the wall. Okay, cool. So we draw the walls way before we do our simulation. Because if you do your simulation and draw the walls, you'll be drawing wall over wall over wall, and that's going to crash your computer. Okay, so we draw them before the simulation. Okay, so self-that create walls like this. Okay, easy peasy. Let's see what we have. Errors. Nope, no errors, and no walls. What? Is it called create walls? Yeah, self-track points. Wait a minute, this didn't work. Track points, self-track points. Oh, wait a minute, equals. My bad. We have to take these track points here and save them. Self-track points equals track points. Okay. Cool. Ah, now it works. Now, race car is on top of the wall. See that? And if we actually move the race, I said if we move the what? It just bugged on me. Wait a minute. Okay. What? It didn't handle the walls or what? I can't pick the car up. It's stuck. There we go. Oh, that's not good. Okay. Yep. See that? Now we put the car here. Can you see the red beams? You can see that whenever we hit the wall, we see red. Yep. So let's just put it in front of us. See that? Red for all of these. And this one right here, can you see it? This is green. Good of this. Oh, my bad. There we go. Can you see a green one here? This green one is not touching the wall. That's pretty accurate. Okay, that's why we use lidars for these kinds of projects instead of cameras. Okay, now it's pretty laggy. Okay, I'm pretty sure it's because I'm running StreamYard and my RAM is just all full. But yeah, now I think there's a little bit of a bug. I don't know if it's because of the CPU, but we have the lidar just looking at one side and not doing the entire 360. Okay, so I'll fix that off camera, and in part 2 this should be fixed. Okay, but yeah, this is the car. Yeah, and you can see we created a wall and a wall can be moved. Okay. And yeah, with these walls, I'm going to draw a track for you. And in part 2, we'll get to make this smart. Okay. We understood how PyBullet works, the basics of PyBullet. Now we can AI this thing. Okay. Cool. Close up time. Any questions? Yeah. There you go. All good. Yeah, all good. A little bit confusing, maybe some parts. Yeah. Again, the whole code is in my GitHub. Okay. So you can find it here. The whole code. Okay. Cool. Hey, thank you so much, Tammy. I hope to see you there. Quakers and cheese. Quakers? Yeah, thanks so much for being here. How does it compare to Webots or Gazebo? I use Gazebo. I think I've used Webots once. For example, let's just do close up time now. If you do Gazebo, it's because you're using ROS. You cannot use Gazebo without ROS. Good thing about PyBullet is that it doesn't use ROS. It's ROS friendly, so whatever you do here, you can use it in ROS, but it's not ROS dependent. Okay, that's a good thing about both Webots. I'm sorry, Gazebo. Webots, I'm not sure. I used it once, a long time ago. I don't remember how it works. It's just a simulator. Okay. The bad thing is it's a Python-based simulator, which is not very good because it can be slow sometimes. Okay, Python is slow compared to C#, C++, all of the Cs. So yeah. But yeah, I would use this PyBullet whenever you're working on Windows. If you're working on Linux, you can use this or Gazebo. Okay, it's up to you. Okay, but again, Gazebo is ROS dependent. PyBullet is not. Cool. Thank you so much for sticking with me. It's so nice. Looking forward for part 2, Tammy. Thank you so much. I'll see you there. Nice. Just before we wrap the stream, please, 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 please. No, thank you, Light Warrior. Great questions, by the way. I just share with you the feedback link, okay? So please go. I'll get to that in a second. Click on continue and then select this one, which is PyBullet. Train on autonomous vehicle with PyBullet part 1. If you liked it, give me a 9, 10 stars. If you didn't like it, give me a 1 or 2. I don't get mad. I don't take it personal. It makes me become a better streamer, okay? And if you have any feedback, just let me know, okay? Or put it here, and you know, coaches will tell me. It's not that they're going to say, "Hey, Quakers and Cheese didn't like it." No, it's not. It's not like that. Everything's anonymous, okay? Cool, awesome. And last thing, close up time. It says, are the C++ C extensions on GitHub enough for installing PyBullet? What do you mean by the C++ C extensions on GitHub? Like what? Like in here? Where's that? What do you mean? Oh, yeah. Like if you're worried about like the Python thing or like this Python. Oh wait, my bad. Like if you're worried about this, like how it looks. It looks like that because of this Dracula theme, okay? And because of, for example, iSort, it helps you sort or organize some things in Python. But there are no Python, for example, PyLens is good to have. It helps you, for example, if you get this wrong, for example, instead of writing enumerate, I write enumerate. It helps you getting that squiggly line under it, but it works without it, okay? But you can install all of the Python extensions, and yeah, you should be all good. Without these extensions, you should be all good too. Like Visual Studio Code actually recognizes Python. You have to go to your path, get your path, put it in Visual Studio, and that's it. Okay. There are a couple of tutorials out there, but yeah, it should be good to go. And yeah, I don't have a lot. VHDL, it's been a while since VHDL. And YAML files, yeah, that's it. Yeah, I have a lot of themes. Okay, just if you want to have this theme, I think it's a Dracula theme. Okay, cool, awesome. Then, if no more questions, thank you so much for joining. I appreciate it, and I'll see you for part 2 on Tuesday. And yeah, there's a Gemini API for a robotics stream tomorrow as well. Yeah, Jocelyn is one of the greatest robotics engineers I've known. She is absolutely good. Yeah, go watch that stream with her. And yeah, no worries. It's recorded on YouTube, so you can watch it there too. And yeah, thank you so much. You learned some things and didn't know Python had classes. Oh, for sure. First thing for Python, classes. That's the greatest thing of Python. Okay, awesome. Justin is more than awesome. Justin is one of the smartest people I know, actually. But yeah, go give her some love. Say hi for her from me tomorrow. And yeah, say that you work with PyBullet with me. And yeah, we should stream together. I'll tell her. I'll ask her to stream something with me. Cool. Awesome. Thank you, Tammy. Is there a way to make your own API for this? Yeah, you can use lots of things. I've done MQTT and Arduino streams, and you can use the same logic for this. Okay, I won't do it now, but yeah, you can do it definitely. Cool, awesome. Thank you so much. My voice is done for the day. But yeah, I appreciate you, and I'll see you on Tuesday. Say hi to Jocelyn for me if you are going to watch her stream. And yeah, enjoy. Take care. Have a nice one. Bye.